Hello, everyone. My name is Shashank Gugnani. The title of my talk today is Understanding the Idiosyncrasies of Real Persistent Memory. This work was done during my PhD at Ohio State, along with colleagues who are now at UC Merced. Persistent memory is a new memory technology that is gaining popularity. There are several PMEM technologies under development. These include PCMEM, STT-RAM, and Crosspoint, to name a few. These technologies have highly variable performance characteristics and internal architectures. So far, only Crosspoint has been commercially used for PMEM and is available as Intel's DCPMM product line. Let's take a quick look at how PMEM is typically organized in a system. There are several components that exist between the CPU and PMEM. First, we have the CPU registers and the store buffer. Then we have the volatile cache hierarchy, typically your L1 to L3 caches. Next, we have the mesh interconnect, such as QPI, which connects the memory to other CPU nodes in a multi-NUMA system. Then we have the memory controllers, which are directly attached to the PMEM DIMMs. PMEM is typically available in two types of persistence modes, ADR and EDADR. In ADR mode, stores must reach the memory controller to be considered persistent. However, in EADR mode, the CPU caches are part of the persistence domain. So stores only need to reach the L1 cache to be considered persistent. So in EADR mode, flushing of cache lines is not necessary for persistence. Now let's take a look at the internal architecture of Intel's DCPMM. The CPU memory controller uses the DDRT protocol to communicate with DCPMM, which operates at a cache line granularity. Access to the crosspoint media is at a coarser granularity of a 256-byte line, which results in a read-modify-write operation for stores, causing write amplification. Optane DIMMs also use an internal cache with an attached prefetcher to buffer reads and writes. The cache is used as a write combining buffer for adjacent stores and lies within the ADR domain. So updates that reach the buffer are persistent. So early evaluation of real persistent memory show that its behavior is more nuanced and idiosyncratic than previously thought. In our work, we found that some PMEM idiosyncrasies are only related to the internal architecture of the memory technology used, while others are related to how PMEM is used and organized in the system. So we believe that system designers should have a proper understanding of the root causes of these idiosyncrasies and how they are applicable to different classes of future PMEM. Current evaluation studies fail to understand and categorize the idiosyncratic behavior of PMEM. In this paper, we considered 4 classes of PMEM. The first class is NVDIMMs, which are simply battery-backed DRAM. The second class is PMEM with an internal cache configured to use a prefetcher. Third is PMEM, which uses media with a higher access granularity than a cache line. And finally, the fourth is Intel's Optane DCPMM. We chose these classes because we believe that current and future PMEM hardware can be broadly divided into these 4 classes. To fully understand the nuanced behavior of PMEM, we designed a micro benchmark suite called PMEM IdioBench. The suite consists of a set of targeted experiments to evaluate PMEM performance and identify its idiosyncrasies. The benchmarks are designed to understand the root cause of idiosyncrasies, as well as quantify and categorize their impact. It also contains tools to analyze low-level PMEM counters and compute relevant metrics, which help identify the root cause of idiosyncrasies. We believe that this benchmark will help guide the design of storage systems by helping developers understand and mitigate performance issues. It will also help system designers handle PMEM idiosyncrasies that are applicable to all classes of PMEM and be aware of ways to optimize their applications for a specific class of PMEM. Finally, our benchmark is open source, so anyone can download it and try it out. In this paper, we identified and categorized 7 interesting PMEM idiosyncrasies listed in this table here. We also provided system design recommendations to mitigate these performance quirks. In this talk, I will cover a couple of them using a case study as an example. To learn more about the complete list, you can refer to our paper. So the first quirk I want to talk about is the high latency of writes to PMEM. The figure on the right shows the latency of a store followed by a cache flush at high concurrency for DRAM and PMEM. You can see that PMEM latency is about 3 times worse than DRAM. Using our benchmark, we identified 2 reasons for this. The first is the slow latency of the crosspoint media itself, while the second is the suboptimal controller design, which is unable to efficiently handle concurrent requests. The main implication of this observation is to avoid protocols with excessive writes to PMEM, such as transactions. The second idiosyncrasy studies the impact of cache flush on PMEM write bandwidth. The figure on the right shows the PMEM write bandwidth when the cache is never explicitly flushed compared with when the cache is flushed after every write. We can see that with explicit inline flushes, we get up to 2 times better bandwidth. So what is the reason behind this? Using our benchmark, we found that there are 2 root causes. First, without explicit flushes, the cache hierarchy evicts cache lines in random order. Second, the prefetcher within PMEM is more suited for sequential I/O. These 2 causes combined result in the observed performance degradation. So the implication here is interesting. Our observation suggests that flushing data from the cache may be beneficial even in EADR mode. We will come back to this point in the case study that I will talk about next. So let's take a look at how we can mitigate the 2 quirks we just discussed using a case study on the design of lock-free persistent data structures. One common approach to design crash-consistent structures is to use transactions. However, transactions on PMEM have high performance overhead due to excessive writes to PMEM and may also require locks. So can we do better? We looked at several different options and found that per-thread micro-logging is a promising approach that can be used. The main idea is to avoid logging changes to data and instead only log high-level operations and its parameters. We applied this approach to 2 data structures, a ring buffer and a linked list. The ring buffer design is a bit complicated, so I will skip this in the interest of time. Interested viewers can refer to our paper to understand its design. I will briefly present the linked list design though. Conceptually, the design of both data structures is essentially the same. So our design is built on top of Harris's algorithm, which uses compare and swap for mutual exclusion. The figure on the right here shows an overview of the design. At the top, we have the physical layout of the linked list. This consists of an array of nodes indexed using a bitmap. Then below, we have per-thread buffers for micro-logging operations. At the bottom, we show the logical view of the linked list. So the idea is to use per-thread buffers to record the status and information of an operation. If there is a crash before the operation is completed, on recovery, we use the information in the buffer to complete the interrupted operations. An important part of the design is to keep the bitmap in DRAM and rebuild it in recovery. This helps prevent persistent memory leaks. This slide presents the results for the ring buffer. The 2 figures here compare the push and pop latency for the implementation that uses transactions with our proposed transaction-free design. We can observe that eliminating transactions improves latency by 3 to 4 times, mostly by avoiding excessive writes to PMEM. We also compared push and pop latency in EADR mode for cases where we don't flush any data from the cache, and when we flush non-critical data, which in this case is just data that is being stored within the ring buffer. We can see that flushing non-critical data improves both average and tail latency by improving the overall persistent memory write bandwidth. So to conclude, we see that persistent memory is gaining popularity, and there are several PMEM technologies in development with varying characteristics. Based on this trend, we proposed PMEM IdioBench, a tool to assist storage system developers. We showed how this benchmark can be used to identify and categorize PMEM idiosyncrasies. We also quantified their impact and provided recommendations to mitigate their impact through a case study. Evaluation of these studies show promising results. With that, I'll conclude. Thank you.